Hello students, welcome to EPG Pathshala. I am Dr. Amarjit Singh from Department of Physics, Himachal Pradesh University. Today we are going to discuss about the module Surface Physics Synthesis Techniques from the paper Solid State Physics. So the students, let us see what we are going to learn in this module. So we are going to learn growth techniques of these surfaces, interfaces and thin films, and we shall learn about application and working principles of chemical vapor deposition, that's called CVD, and we will learn a technique called Langmuir-Blodgett techniques. These are completely different techniques applied in completely different field of surface science. CVD is usually used for hard condensed matter systems, and Langmuir-Blodgett technique is used in soft condensed matter physics. And we shall learn how to deposit single layer and multi-layers from this Langmuir-Blodgett techniques. So let me just discuss with you or walk you through some of the very important techniques of this thin film surfaces and interfaces. So as we need to grow thin films and nanostructures, there are a range of techniques and methods. One is called let us separate it into branches of hard condensed matter and soft condensed matter. So for hard condensed matter, the devices are chemical vapor deposition and metal organic CVD, which is advanced technique, then CVD, and the molecular beam epitaxy. So this molecular beam epitaxy, one can deposit the film or nanostructure layer by layer. So you can really put atom by atom construction using this MBE technique, and this is ultra high vacuum technique, and so very costly technique also, but very advanced technique for preparing nanostructures, surfaces, thin films in hard condensed matter, and laser ablation techniques. In soft matter and biological systems, the techniques are Langmuir-Blodgett technique, spin coating technique, Dr. Blade, and spray coating, dip coating. These are the techniques in soft condensed matter. So in this module we will pick up this hard condensed matter technique, which is CVD, and another is Langmuir-Blodgett technique, which is used for soft condensed matter systems. So chemical vapor deposition. So what is chemical vapor deposition? Deposition can also take place due to the chemical reaction between some reactants on the substrate. In this case, reactant gases, which we call precursor, are pumped into a reaction chamber or a reactor. Under right conditions means temperature and pressure, they undergo a reaction at the substrate. On the products of this reactor, one of the products of the reactant's gas deposited on the substrates, and these are kind of byproducts. They are pumped out from the system, which are undesired. The key parameters are the chemical reactant rates, gas transport and diffusion. These are the parameters which control the growth of a film on a substrate. CVD. Now you see that on this slide we have shown the principal working diagram of a CVD. So this has a tube, and this tube is contained in some oven, so that we can control the temperature of this tube, and there is a gas inlet, and then there is a place where substrate is placed, and this is a gas outlet. So from the gas inlet here, this precursor gas is flown, and it reacts on the surface, and then the gases, undesired gases, come out of this tube. And a enlarged view of this sample is shown here on the right, and you can see that it's a substrate surface, the precursor gas flow is coming, and the adsorption phenomena is taking place on the surface, and then chemical, they can if there are different kinds of gases, they can chemically react and leave some gases out, thrown out. So that way we grow a different kind of structure or substance on a surface, a very thin film on a substrate. Working of CVD. Here it has been shown in slightly more elaborate way. So I will just tell the process in step by step. So connective and diffusive transport of reactants to the reaction zone. First we take that gas, and then in the next stage gas phase reactions takes place, and then we transport the reactants to the substrate surface, and in the next phase chemical and physical adsorption takes place, and followed by surface reactions leading to the film formations, and there can also be a diffusion which can be taking place, and there can be desorption of this after this chemical reaction there is a desorption of this volatile products, and they are just pumped out, and collective and diffusive transport of byproducts away from the reaction zone. So in these steps, in this diagram it has been shown in more elaborate way that some of the reactants happens in a gas phase, and this adsorption take place, and then this atoms can diffuse along the surface and form a layer as shown here, and the undesired molecules, they dissolve and go out of this tube. Requirement for the CVD process. Now when we are depositing a film through this CVD, chemical vapor deposition processes, so what are the requirements? The precursors have to be volatile gases. Example is SiH4, and this is called silane, is a popular precursor to deposit silicon if you want to deposit silicon. So this should be in a gaseous form, and the chemical reactions need to be thermodynamically predicted to result in a solid film. So there should we know that this definite reaction is going to occur at the interface, whose products is known to us. This means that there should be an energy advantage for the desired reaction to occur, meaning the Gibbs free energy has to decrease. T and temperature and pressure can be adjusted for minimizing this Gibbs free energy. The byproducts which are not needed to be volatile gases, so that we can pump them out. Goes into silicon and hydrogen, where hydrogen gas goes out, and similarly NiCO4 in gaseous forms, this decompose into nickel and cobalt, and we can deposit a different varieties of substance, as you can see here: aluminium, titanium, molybdenum, iron, boron, etc. So next type of another form of reaction is what is called reduction. So in this we use hydrogen gas to reduce halides, carbonyl halides, and oxyhalides. So SiCl4, and we reduce it with hydrogen to get silicon and HCl in the gas form, it goes out. And similarly WF6 in gaseous form, it reacts with hydrogen, and it deposits tungsten, and HF gas goes out. Similarly we can deposit these materials as shown below. So in this slide, the another form of reactions which are shown is one is the oxidation and compound formation. So in oxidation, we oxidize these materials like silicon hydride, and to get silicon oxide layer, and this H2 gas goes out. And similarly aluminium chloride, we oxidize it to Al2O2. So if we would like to deposit some oxides, this is the way, and we can also deposit TiO2, Ta2O5, SNO2, and ZNO. So these are interesting materials in
in nanoscience and technology. And the compound formation like silicon carbide, boron nitride, these have been very interesting semiconducting materials. So these below are the processes where silicon chloride with a reaction with methane turns into silicon carbide, and boron fluoride with reacting with.
Okay, so let me introduce you with the Langmuir-Blodgett techniques. It is used to prepare thin films of surfactant and lipids. A uniform monolayer can be spread on a liquid surface. A monolayer of surfactants and lipids can be transferred on the solid surface also. And not only that, several multilayers can be deposited on a solid surface through a software controlled system. So this is a very popular technique for growing multilayers of lipids and surfactants in soft condensed matter field.
What a surfactant or a lipid system looks like. Now, as you can see that on the diagram, a surfactant or a lipid is an amphiphilic molecule with the hydrophobic tail and hydrophilic head group. Using the appropriate solvent, the surfactants are dissolved to prepare solutions. Now you can see that in this structure on the right hand side there is a sodium atom and carbon on this head group, and there is a hydrocarbon tail of CH2, 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 CH2 like this. So this can be very long or short. So this tail is usually hydrophobic, or it when you put it inside the water, this hydrophilic tail, this hydrophilic head group would like to stay in the water, and this hydrophobic tail it goes out of water. So this molecule has a bipolar character that when you put it in the water, it decides which side to stay in the water, and this hydrophilic head group stays and this hydrophobic group goes out. And then we dissolve this material, or we should say this lipid surfactant in a given solvent. So there is a usually the organic solvents are used for this, such as chloroform or other things, in which the surfactant molecules can be dissolved properly before spreading into the water trough. In this slide we are demonstrating the working of Langmuir-Blodgett system. So solution are prepared on the are spread on the liquid surface on the trough through a syringe as shown in the left hand side diagram. So we prepared the solution already, and there is a water in this trough, and there are two barriers there, and we just put some few drops of this solution so that this amphiphilic molecule is spread on the surface, and their concentration is calculated in such a way so that we cover only a monolayer of molecule covers the entire surface. We cannot take extremely large concentrations, because then it will be more than it can cover the surface. So there will be problem that we will be encountering. We cannot really talk about the monolayer. So we have to use a very small concentrations here, so that we are sure that only a single monolayer of surfactant or less is spread on the water surface. On the right hand side, this is some commercial equipment of the LB system which has been shown. This trough which you see, it is made of Teflon, and the water is filled in this trough, and these are two barriers which are motorable barriers. With the help of software and these motors, these barriers can be compressed or they can be expanded outside. And to measure the surface tension of the surface, there is a system called this film balanced technique. So this measures basically the force and gives us the value of the surface tension. And you can see that there is also a pit inside. So this pit is used for dipping the substrate, because if you want to transport this film on a solid surface, you need to dip the surface, and for dipping you need to have some deep kind of well. So in the middle you can see the deep kind of well is there. So when we spread some molecules on the water, so how to measure the presence of surfactant layer on the water surface? So one of the way is measuring the surface tension. As you know that surface tension of the pure water is maximum. When you put something on the surface, some surfactant, you only reduce the surface tension, and therefore this equation which gives pi is equal to gamma H2O minus gamma. So this last gamma is when you spread something on the surface. So this is how we define a surface pressure, or in other words, if the concentration of the surfactant is increasing on the surface, this surface pressure will increase. So with the measurement of this surface pressure, we will understand that the film is growing or there on the surface. So on this slide we discuss how surface pressure is measured. So this method is called Wilhelmy plate method. On the left hand side you see the Wilhelmy plate. This is a small plate. We can use it. It's usually made of tungsten, but we can also use simply a paper here. A blotting paper can also be used. Now in this diagram you see that this film has a D thickness, and it has its own weight, and this is how the water meniscus looks like when you dip it inside the water. So on the right hand side this equation shows that what kind of forces are working on this plate. So there is a weight of this plate which is always working downwards, and then there is a Archimedes force. The next is Archimedes force. So Archimedes force is working upwards. It's the buoyancy, and the capillary force which is also pulling it down, as you see this FC on the right hand side on the figure. So when you change something on the surface, this weight and Archimedes force, they remain same. Only what changes is this capillary force, which include the gamma there. So any change in the surface tension of this liquid surface is perceived through it, and that is recorded in form of some force in using this balance, and which is can be converted into a surface pressure as written on the top. So on this slide we talk about measuring the isotherm, as you also see in the picture. The question is, when we spread the surfactant molecules on the surface, so how do we know whether they are in gas phase or liquid or solid form? So initially as we discussed earlier, we make sure that the concentration of this molecule is very small on the surface, so that on the surface they just move like a gas in two dimension. They are trapped on the surface, of course, but they have no interaction among themselves, just like gas molecules do not have. So then we start compressing the barriers and start reducing the surface volume. Naturally these molecules will come together, and this diagram which plot a molecular area and the surface pressure on y-axis. So as we reduce this molecular area, we can see that the surface pressure is very low. So they are in a gas phase. So when they begin to interact, you can see the next slope rise. This is some sort of liquid form. So in this liquid form there is no structure, a definite structure among this surfactant molecules on the water surface. They can easily flow like liquid along the surface. So in other words, the structure of this two dimension is just a liquid like. And then when we compress it further, and we can see that finally this rise in surface pressure is very high, very strong. So this compressibility is solid like, so that even when you reduce even a small amount of area, you have a large pressure, increase in large pressure. So at this stage, this surfactant molecules are organized in a pattern, just like solid atoms and molecules are organized in a given pattern which we call lattice. So here the surfactants also are organized on a surface in form of lattice, this two-dimensional lattice. So this has all sorts of symmetries of two-dimensional lattice. And finally, if you compress it further, you can break this monolayer, and this is what is called collapse of the monolayer. So you can really break this layer into that, and so we have to be very careful while making a monolayer so that not to break this film. So on this slide now we will show or discuss how this monolayer of surfactant can be deposited on a solid surface. Monolayer or multilayers can be deposited. So this has been shown diagrammatically. First we put surfactant on the surface of water through syringe, and then we compress this barrier to make it a solid film. As you can see below on the left hand side, it's a monolayer of surfactant in a well organized pattern. After this is formed, now we can deposit it on a hydrophobic surface. So when we see these figures on the right hand side, you can see that we have a vertical substrate which we dip inside the water. When we will dip it inside, you can see that as the surface is hydrophobic, the hydrophobic tails of the surfactant will stick to this substrate in this fashion, and they will just get deposited on the solid surface. In this next phase, when you lift up this surface, in the process of lifting up, there is a hydrophilic head group outside. So they will attract the hydrophilic head group from the layer, and they deposit another layer. So this is a kind of bilayer you can deposit in this way. Here it is important to mention that during this process we make sure that the pressure of this system or this layer remains constant, because as we are lifting up, so we are removing some of the materials, the pressure will drop. So we just keep the pressure constant with the help of software. So you see, this is the way how we can deposit a film, but instead of depositing a monolayer, here we have deposited a bilayer. So if you really want to deposit a monolayer of substance, what you have to do is you have to keep this substrate already dipped inside the liquid before we pour the substrate on the barrier, and just by lifting up the substrate in one stroke will deposit a single monolayer of surfactant on the surface. But in that case our surface should be hydrophilic, because then hydrophilic head group will attract to the surface and will lead to the deposition of single monolayer. Now in this way we can deposit so many layers or multi-layers in this form. We can keep on dipping and removing this substrate in a cyclic way. We dip it and remove it, dip it and remove it. In this cyclic fashion we always add 2 layers. So then it is even possible to deposit even 50 or more than 50 layers of this LB film, and then we can do further experiment on this film as they are transported on the solid surface. Vertical and horizontal deposition. So in this slide, with the help of these 2 cartoons, we show that we can deposit in vertical fashion as well as in horizontal way. So in left hand side you can see that the substrate was already inside the liquid before the layer was prepared on the surface, and when you lift it up in a single stroke you will see that a monolayer get deposited on the surface. Usually the quality of one side of surface is very high and other side is rough, so we can use the characterization on the one side where it is very low roughness is there. So on right hand side you can see that we can also use the deposition technique with in a horizontal way. Here we have a hydrophobic surface, and we just bring it close to the layer and just touch the water surface from above, and this hydrophobic tail will stick to this hydrophobic surface, and in this way we will get a deposition of a monolayer in a different way. Now you can see that the structure of this monolayer is different when you deposit on a hydrophobic surface and hydrophilic surface. In hydrophilic surface, it is the head group which is adsorbed onto the surface, and on hydrophobic surface it is the tail of this amphiphilic molecule which is adsorbed onto the surface. So in whatever way you want to prepare the film, accordingly you use this vertical method or horizontal method, but this vertical method is more popular. And one important thing also here to note in mind is this, that in vertical deposition we need to make this substrate extremely parallel to the surface, which is sometimes usually difficult. And in vertical dipping method, even if this angle is slightly tilted from vertical, it works very fine. So this vertical deposition technique is usually preferred over this horizontal deposition technique.
So students, let us summarize what we have learned in this module. First, a CVD is a technique used to synthesize ultra-thin films of semiconductors, metals on chosen substrates. CVD can also be used to grow nanostructures on solid surface, and on the other hand, in soft condensed matters, Langmuir-Blodgett technique is used to grow monolayer of surfactant molecules, and different phases such as gas, liquid and solid can be identified using the surface pressure isotherms. So we learned about surface pressure isotherm, and we saw that how from the help of isotherm we can identify different phases of this surfactant molecules. Layers of surfactant can be transferred on solid surfaces by vertical dipping and horizontal lifting method. Multilayers can be deposited using many cycles of this deposition using software control method, and we also learned that there are two techniques of this deposition. One is vertical deposition and another is horizontal deposition. So students, you see we have briefly touched upon these two devices, but if you want to go to the details of this, one need to study them in the prescribed literature, and there are lot more techniques than those which has been discussed here.